So let's examine sound as a wave. We're all quite familiar with sending information using sound. In fact, listening to this presentation right now, you're doing just that, using sound to get some information. And that's a very important property that waves have, the ability to transmit information as the wave moves along. But what kind of a wave is sound? We know that sound can move through lots of different media. It can move through a window, sound can come through a wall, it can even move underwater. We're quite familiar with whales, for example, sending sounds over long distances through water to communicate. But for us, when we say sound, at the moment we're going to restrict ourselves to mean sound moving in air. Now, what happens when sound moves through air? Well, if you look at the graphic on your screen right now, you'll see there's a whole bunch of small colourful dots being moved around. That's indicating what happens to the atoms and molecules that make up the air. That little blue line moving backwards and forwards is pushing on those atoms and molecules and creating a little bunching effect. And that little bunch of atoms collides with the atoms next to it, and that bunch moves along. If you look carefully at those coloured dots, you can see they're moving backwards and forwards in the same direction as the wave that's moving along. That tells us that sound is indeed a longitudinal wave. But what's happening as that bunching and unbunching occurs? Well, let's look in a little bit more detail at what's going on. So here we're looking at a snapshot of those atoms and molecules moving in the air. You can see there are regions here where there aren't so many of them, and other regions here where they've kind of bunched up. Remember, this wave was moving along to the right. Now, in these regions where they're bunched up, we refer to that as a compression. The atoms have been compressed into that region of space. And that actually has high pressure in that particular region of space. So there is an example of one region of compression. In these regions here where there aren't so many atoms and molecules, we call that a rarefaction. That is where the air is rarefied, or a region of low pressure. And so our wave is now made up, our sound wave is made up, of regions of compression and regions of rarefaction. In fact, we can think of our wave as a compression wave. These compressions are moving along. Another way to think of it is it's a pressure wave, regions of high and low pressure. And so underneath where this wave graph is indicated, we could put some axes on here and say that this is in fact a graph of pressure where we're oscillating around some average pressure. And in our compression regions we have a high pressure, and in our rarefaction regions we have a low pressure, oscillating backwards and forwards from the average background pressure. This is indeed our pressure or compression wave as a sound wave. We can again see we have the same property here between identical parts of the wave. That would be indicated by the wavelength lambda, and how many waves we had per second would be the frequency. Which of course brings us to the speed of the wave. How fast does this compression wave move through the air? It turns out that depends upon the properties of the air. Things like the density of the air, the temperature of the air, even things like the humidity in the air. But for normal conditions, the speed of sound in air is around 330 metres per second. Now that sounds quite fast, 330 metres per second. It would be very fast for any vehicle you would travel in, but indeed compared to other waves like light, for example, it's not so fast at all. In fact, many of you might have experiences perhaps sitting at a concert where you see the things on stage moving before you hear the sound. And that's telling you that the light wave arrived at you before the sound wave arrived at you. Quite familiar with that idea of measuring the speed. Another interesting thing you could try is when you see a lightning flash and you know sometime you have to wait for the thunder to arrive. Again, that's the difference between the speed of the light and the speed of the sound. Given that sound will travel at around 330 metres per second, every 3 seconds the sound has travelled about 1 kilometre. So if you see a lightning flash and then you count slowly, one number per second, every 3 that you count is 1 kilometre away that lightning strike occurred. So we're going to continue in the next topic to look at some of the ideas about sound, in particular about how our ears perceive sound. Which of these properties become important when we're trying to understand the sensation of a sound wave?